Hi, I'm Simone Foti from the Computer Assisted Surgery Group at the University College London. In this presentation, I'm going to discuss our work on 3D shape variational autoencoder latent disentanglement via mini-batch feature swapping for bodies and faces, which introduces a novel approach to learn a more disentangled, interpretable, and structured latent representation for 3D variational autoencoders. Let's assume we want to generate the face of a digital human. The first step is surely going to be the creation of 3D shape of the face. But how would you create the 3D shape of a face? If you are an experienced artist, you may decide to start sculpting the face from scratch. But if you don't have that level of confidence with 3D software because you're not an artist, or if you just want to start from an existing face, you could use a data-driven generative model instead. One of the most common generative models currently available in literature is the variational autoencoder. Once the model is trained, the generator can generate new shapes from random vectors. However, with a simple GUI, you could also change the values of the latent variables and try to control the generation process. But let's see what happens to the generated shapes when we traverse the latent variables. In this video, we report vertex displacements occurring during the traversals using a color map. Blue regions correspond to areas where vertex positions don't change, and yellow regions represent big vertex displacements. As you can see, unfortunately, the creation of local shape features is impossible. The generative coefficients lack semantic meaning and determine global changes. It is also difficult to know which latent variables control different features, and the latent variables are entangled between each other. Therefore, in this work, we propose a simple yet effective approach to overcome these limitations. We start by redefining how the input data are grouped into mini-batches. Let's assume that we load 4 head meshes. From these 4 meshes, we can create a matrix where the original heads are placed on the diagonal and where the remaining elements are filled by copying the heads across the rows. At every iteration, we create a mini-batch and we select an arbitrary facial feature. In this case, we select the nose, but at the following iteration, we could select the mouth, the eyes, or another facial feature. We then swap the selected feature across columns. Now we have a mini-batch where shapes across rows are the same, but with a different nose. Across columns, the shapes are different, but they have the same nose. We can partition the latent vectors in as many subsets of latent variables as facial features. During training, we can use a triplet-like loss to make sure that the subset of latent variables controlling the nose are similar across columns and different across rows. At the same time, we can also force the latent variables controlling all the other features to be similar across rows and different across columns. If we now observe the effects caused by traversing the latent variables, we see that our method can better disentangle the latent representation. This is particularly evident when we observe the faces rendered with a color map proportional to the vertex displacements, because with our method, only a specific area changes shapes and becomes yellow. On the other hand, traversing a latent variable of a state-of-the-art method determines global changes in the generated shape, with multiple features turning yellow. Therefore, none of the state-of-the-art variational autoencoders here represented achieve similar levels of disentanglement and control over the local features. If we then encode two shapes and generate new heads by linearly interpolating between the two encoded latent vectors, we clearly see that while other methods generate random faces that are not intermediate identities, our method can control one feature at a time and generates only meshes plausibly interpolated between the source and the target mesh. Thanks to its semantically meaningful and structured latent representation, our method can also perform latent interpolations on subsets of latent variables controlling the identity of a subject. As you can see from the generated shapes, every time a subset of variables is interpolated, only one facial feature is changed. If you have any questions, feel free to reach out or meet me in person at the poster session.